Welcome to my presentation about multi-robot system prototyping for cooperative control in robot-assisted spine surgery. In this project, we designed a robotic platform for collision-aware continuous object tracking. Nowadays, over 4.83 million spine surgeries are performed annually around the world. Robot-assisted spine surgery has been clinically validated worldwide, with improved precision, patient outcomes, and many others. Currently, there are 4 main spine robotic systems commercially available. All of those robotic systems can be simplified as the model demonstrated in this figure. They all highly rely on fiducial markers. The additional marker insertion not only increases the infection risk, but also fails the tracking system when it is blocked by the surgeon movement. To resolve these issues, previous research has been investigated, where a desk camera was used to train a network for markerless robotic tracking. However, desk camera is usually optimized for use in close distances, and thus it cannot be placed far away to physically avoid obstacles. Obstacle avoidance is therefore crucial in robotic tracking system. In previous research, the obstacle was only simplified as a point, and only one obstacle can be considered. In today's work, I will talk about the robotic systems I developed to address these challenges. First, let's come to robotic hand-eye calibration. The first part of the project develops a ROS2 hand-eye calibration package, including algorithms such as camera intrinsic calibration, Aruco marker pose estimation, robot state estimation, and finally, hand-eye estimation calculation. This package fills a gap in the availability of open-source options in ROS2, and it is universal for both DEX and RGB cameras. To prove the algorithm accuracy, we first developed a pipeline in simulation, where the camera intrinsics were first calibrated. We then used the algorithm to calculate the result of hand-eye transformation. As in simulation, the camera was manually defined. Therefore, it can be used as a ground truth to evaluate the algorithm. Then we replicated the exact scenario in real experiment to ensure the accuracy. The following video demonstrates our full hand-eye calibration pipeline. Firstly, we control the robot to take distinctive samples. From the third samples on, we calculated the hand-eye transformation result, and we compare it with the ground truth for each of them. We found that with these poses, after 9 samples, we can ensure the error to converge to 0. We then visualized this calculated transformation, and we found that it almost overlaid with the ground truth. In the real experiment, we used admittance control to control the robot to take samples. We then replicated the robot and marker poses in real experiments, similar to those 9 poses in simulation. And we found that the calculated transformation positions and poses is quantitatively true according to the real-sense camera documentation. Secondly, I would like to talk about object tracking. Firstly, we modify the marker estimation node to output the marker poses. Then we design a coordinate transformation pipeline to calculate the robot's elevated poses to point normal to the marker while keeping a constant distance away. For knee detection, we use a knee joint depth image segmentation network, and we implemented a similar pipeline for coordinate transformation. We visualize the calculated knee poses relative to the robot warframe. Compared with the real experiment, we found that our knee detection and transformation is quantitatively true. Now I will talk about obstacle avoidance. Common approaches to generate collision-free motion for robot arm includes using graph planner or trajectory optimization. For graph planner, shorter paths take several seconds and it's hard to encode additional cost terms. Trajectory optimization is prone to getting stuck in local minima. It also takes 2 to 3 seconds to plan. cuRobo overcomes this hurdle by putting the full motion generation stack on the GPU. Research shows that it is 80 to 90 times faster than state-of-the-art tracked OPT from Tesseract. In this work, we made use of the advantage of CUDA acceleration, and we implemented an obstacle avoidance pipeline as follows. We first set the flag to coordinate motion generation and execution. When previous motion is executed, we trigger the marker or need detection node. We then add an additional check to see if the robot needs to move to track the object. If so, we use cuRobo to generate collision-free motions. Only when the motion is generated will the robot be triggered to execute those motions. And the whole pipeline will only stop when human interrupted. More details during the motion generation are shown here. We use ISSing to generate collision spheres, and we got their positions and radius to represent the robot. Then collision query is implemented between the robot sphere and either cuboid, sphere, cylinder, and additional robot mesh. The video on the right visualizes the parallel computing motion generation, where inverse kinematics were performed in multiple positions at the same time. In order to avoid the second robot in real experiment, we need to have its precise mesh representation. We developed a mesh transformation algorithm by replicating the robot pose in simulation, and we read its kinematic transformation from simulation. We also perform experiments to evaluate how well robot tracks the generating motions. Because large position deviation causes the robot to still collide with the environment, and inadequate velocity tracking increases the robot motion time and affects the following task cycle. We then studied the simple robot motion demonstrated in this video. We show the left figure being the theoretical motion and the right figure being the recorded real robot motion at 100 Hz. Because the acceleration and jerk data are not available from the ROS2 feedback, we perform numerical differentiation to calculate them. This time discretization introduced significant noise. We then perform a series of moving average filter, and the process data, the real motion, is quantitatively similar to the theory. We also evaluated more detailed errors by subtracting both figures, and the result shows each joint only has 1.22 degree deviation on average, and the velocity tracking is even more accurate. To evaluate the obstacle avoidance performance, we studied the simple motion by moving from 2 points at the same plane. We know naturally that the optical smooth and short motion is moving along a circle on the same plane. We then perform experiment on the real robot, and the result shows that the robot is able to avoid obstacles while keeping the motion path smooth and short. We can easily see from the position figure that the two robot has only a slight change of joint A2 motion when the obstacle was placed in the middle. In this video, we demonstrated the real obstacle avoidance performance experiment. To show that the robot is able to move freely around the obstacle, we developed an algorithm to randomly generate goal poses around the obstacle. We then asked the robot to reach these randomly generated positions. The result shows that the robot is able to avoid both simple and complex obstacle environments while generating motions within 50 milliseconds and 500 milliseconds with RTX 4060 GPU. We recorded the motion solve time, delay, and execution time, and we also compare the performance with better 4090 GPU. Result shows that in a single cuboid obstacle environment, the motion generation only accounts for 1.3% of full motion time, while in more complex robot as an obstacle environment, motion solve time took around 500 milliseconds. Using 4090 GPU can improve the overall performance by around 30%. Next, let's talk about collision-aware tracking. We designed a tracking experiment where the second robot held a marker with a predefined motion. In order to know how well our motion generation algorithms are, we evaluated two aspects: how well the robot traces overlap with each other, and was the distance between the two robot end effector constant. As shown in the video, we studied two simple experiments, one for tracking a straight line and the other for tracking the imperial letter I. We then recorded two robots' end effector positions and orientations as the two videos showing at the bottom. From the figures and the videos, we can easily find that the robot can accurately follow both simple and complex patterns, while keeping the movement within 0.4 meters in straight-line experiment and 0.01 to 0.02 meters in eye-letter tracking experiment. We also studied the anti-feather distance during tracking, and we found that the deviation is negligible and stable. Finally, we compare our method in object tracking with popular motion planning library called Movie. The Movie uses the classic RT Connect graph planner to generate motions, and we can easily find that with cuRobo, tracking can be extremely smooth and stable, with minimum path lengths and smooth motion. Here, we demonstrated two videos of our multi-robot system for collision-aware tracking. The video on the left shows the marker tracking without collision with the second robot, while the video on the right shows a demo where we plug in the knee joint depth image segmentation network. The robot is then able to track the knee without any marker, perform the markerless tracking in real time. Finally, let's talk about limitations and future work. Firstly, our hand-eye calibration doesn't make use of the depth sensor to further improve the accuracy. In scenarios where there is a mismatch between depth and color frames, and with color image resolution is too slow, we will need another 3D method for calibration. This can be, for example, a sphere model. Another important work lies on the online obstacle avoidance. In real surgical scenario, the second robot needs to be controlled by the surgeon to perform surgery, and therefore it moves. Before, we didn't implement the mesh transformation automatically. If the second robot is continuously moving, obtaining its real-time kinematic links is essential. In the future, we can implement the ROS2 topic to read this transformation in relation in real time. And instead of mesh transformations, we should also replace the mesh with spheres. This can bring the collision query to simple sphere-sphere distance, avoiding the mesh query, which largely increases the solve time. And with this method, we can finally put the whole system on the fly. Moreover, future work can also introduce GPU-accelerated side distance field reconstruction. With additional depth camera, we can segment the dynamic human being and add it to collision query. With this, we can also avoid surgeons in the operating theater in real time. As you can see in the video, when the depth camera detects the surgeon, the robot will try to avoid the surgeon with the side distance field reconstruction. In conclusion, my unread thesis mainly introduced 4 research contributions. If you want to revisit the above content, I also wrote a website where you can scan the QR code for more information. Thank you.